Hey, it's Mrs. KJ going over 5.03 Review Reaction Rates. Review concepts presented in the lessons, reaction rates and energy of activation, and factors affecting reaction rates. Understanding why reactions occur as they do is important to chemists. This review lesson looks at reaction rates, specifically the energy involved in a reaction, and the factors that influence the rates of reactions. Goals demonstrate mastery of important knowledge in the lesson, reaction rates, and energy of activation, and factors affecting reaction rates. So again, you can download the student guide. Key concepts in reaction rates and energy of activation. So again, as a reminder, I suggest that you copy paste this and then, either delete or cover up some keywords and see if you can fill them in, and do it tomorrow after you've practiced this, or cover it up with paper right now and see if you can figure some out. Reactant molecules collide together in reactions. Those reactant molecules colliding with sufficient speed or energy and the right orientation or direction will form an activated complex during the transition state that will separate into products. So remember, you have the reactants, they make a big blob, and then they become the products. The energy difference between the activated complex and the reactants is called the activation energy, or E sub A. Reactions with low activation energy are more likely to proceed than those with high activation energy. Reaction rate is expressed as the decrease in reactant concentration over time or an increase in product concentration over time in a system of molecules. Chemical reaction, time it takes is the reaction rate. Chemical reactions begin with reactants, becoming activated complex, becoming products. Key concepts in factors affecting reaction rates. Hopefully you can tell me all four of them without looking at the screen. Temperature, concentration, surface area, pressure, and of course, catalysts and inhibitors. A number of factors affect the rate of a system's chemical reaction. An increase in temperature or pressure will increase a system's reaction rate. The larger the surface area on a substance, the greater the rate of system change. So if I want more surface area, do I have bigger or smaller pieces? Smaller pieces. Same amount, smaller pieces. The higher the concentration of reactants, the greater the rate of a system's change. A catalyst is a substance that increases the rate of reaction without being used up. All the effects of these factors on reaction rates can be explained by collision theory. So remember, they have to collide in order to react. Organize key concepts involving chemical reactions and reaction rates. All right, so go ahead. Chemical reaction, the time it takes. So which one should that be? Are affected by temperature, concentration, blank, and pressure. What should it be? And chemical reactions begin with reactants becoming, obviously the only one left, activated complex becoming products. And now we'll look at the book to review a few other things. Again, the book, if you forget how to get there, you have to scroll up, and it's problems and solutions and a lab guide. And you just click here, and it opens it up in a new window. And from there, we can find the correct area that we need to go through, meaning, there we go. Down there, you can see where it says cover, and you can just type in the number of the page. Right, so problem set 82, we're on page 184. Reaction rates and energy of activation. Different chemical reactions happen at different rates, and those rates depend on many factors. Chemists often need to know how quickly a reaction will proceed. They define the rate of a chemical reaction in two ways: the rate of increase in concentration of products over time, or the rate of decrease in concentration of reactants over time. In other words, your reactants are getting used up, so there's going to be less of them. Your products are being made, so there's going to be more of them. The rate of a chemical reaction is affected by the frequency and velocity with which reactants collide to form activated complex, or the big blob that they need to come together before they make a product. The activated complex is the intermediate species between the reactants and the products. Anything that affects the collisions between reactant particles, such as temperature, concentration, surface area, or the presence of a catalyst, will affect the rate of a chemical reaction. The difference between the energy of the reactants and the energy of the activated complex is the activation energy of the reaction. So again, it takes energy for the reaction to occur. All right, objectives: use collision theory and energy versus time plots to explain reaction rates and activation energy. Know how reaction rates are expressed. Remember, reaction rate. The rate or speed of a reaction is defined as the change in concentration of products or reactants over time. So, more products, less reactants, because the reactants are turning into the products. According to collision theory, a chemical reaction occurs only when reactant particles, so the atoms, ions, or molecules, collide in the correct orientation, like a lock in the key. The key cannot be upside down, so correct orientation, and with sufficient energy to overcome the activation energy or energy barrier of the reaction. So they're sitting here, and they need this much energy in order to, boom, make that big blob, the activated complex, during the transition state, and then become products. Reactions with high activation energies are generally less likely to occur than those with lower activation energies. In general, anything that increases the number or velocity of collisions between reactant particles increases the rate of a chemical reaction. All right, interpretive reaction diagrams. So we have energy increasing and reaction process. The diagram shows energy versus reaction process for a chemical reaction. Is the reaction endothermic or exothermic? What do A and B represent? Okay, endo means in, exo means out. So let's look. Our energy of the reactants is up here. Let's just make up a number. Let's say it's 100. Okay, then boom, I need to go up. So, okay, 150. And then boom, I end at about an energy of 10. So which has more energy, my reactants or my products? My reactants have more energy. So was energy in or energy out? Energy was out because there's less energy at the end. So is it exo or endo? It is exothermic. Okay? The energy of the reactants is greater than the energy of products, so the reaction is exothermic. Okay? Now what is this A? That's that hump that it has to go over, or the hill, and that's that extra energy, and that's the activation energy. B. Okay, we haven't talked about this one yet, but let's look at what it's pointing to. Here's the energy of the reactants. Here's the energy of the products. Oh, it's how much energy was given off or let out because it was exothermic. So it started with 100, it went down to 10, 100 minus 10, it gave out 90. Now, if you're sitting here going, wait a minute, where is she getting 110 from? I just made up those numbers because when you do graphs without numbers, sometimes it helps you to understand more just to make up some numbers. So I made up 100 because it's a nice easy number. This number was obviously much lower, so I made another easy number like 10. Also, when you do graphs, always make sure you read what the y and the x-axis is. All right. So let's see what else they said. So A represents the energy hump or barrier that the reactants must surpass to react. Therefore, A must represent the activation energy for the reaction. B represents the difference in energy between the reactants and products. So it represents the delta H, or the change in enthalpy for the reaction. Relate collision theory to reaction rates. Tip: increasing surface area increases the rate of reaction, but it does not change the activation energy or the enthalpy change, that delta H, for the reaction. A small spark can cause coal dust in the air to react explosively, presenting a hazard in places where coal is mined or processed. A lump of coal, on the other hand, burns slowly and safely. In each case, the reaction is the same. Carbon from the coal plus oxygen gas yields carbon dioxide. Explain in terms of collision theory why the rates of reaction are so different for different forms of coal. Okay, so collision theory, they're colliding. When is there more collisions? Okay, hopefully you said when there's more surface area and when the pieces are bigger or smaller, smaller. Reaction rate increases with the frequency of collisions between the reactants increase. The frequency of collision increases as surface area increases. When an object like a lump of coal is pulverized into dust, its surface area increases, but again it's the same amount. Oxygen will come in contact with carbon more often if the surface area of the carbon or coal is increased. Therefore, the coal dust will react more readily than the lump of coal because the increased surface area of the coal dust will enable more collisions between the carbon and oxygen atoms. All right, question number 1. The diagram below is a graph of energy versus reaction process for chemical reaction. Is the reaction endo or exothermic? Explain your answer. Hit pause, get your answer. Okay, here's the answer. My energy of reactants is very low. My energy of products is much higher. So I brought energy in, right? I had to increase the energy. I brought energy in. So in would be endothermic. Again, exothermic is the opposite. So exothermic is going to look like this. The products have less energy. In this example, the products have more energy. Question 2, how is the overall reaction rate related to the change in concentration of reactants? How is rate related to the change in concentration of products? So hit pause, get your answer, and the answer is reaction rate. Concentration of reactants is going to go down. We're going to use up those reactants when we are making our chemical reaction. The concentration of products is going to increase. And I could show this on this graph. Which line would be the products, the blue or the red? Products are going to increase over time, so it's the blue line. Reactants are going to decrease over time because they're getting used up. Explain in terms of collision theory why adding heat can increase the rate of a reaction. Hit pause, get your answer. The answer is the more heat you have, the more energy, the faster the molecules are moving. The faster they're moving, the more collisions they're going to have. So your percentage of effective collisions or colliding in the correct orientation are also increased. Okay, the next lesson, factors affecting rates of reaction, problem set 83. All right, our second set of problems, a cookie recipe says to mix the ingredients, hint reactants, and bake the cookies for 10 minutes at 350 degrees Fahrenheit, but a student misreads the recipe and bakes the cookies for 10 minutes at 305 degrees. How will the student's mistake most likely affect the cookies? Explain your answer. Hit pause. The answer is obviously they're going to be underdone, right? They're not going to be totally cooked because we didn't cook them at a high enough temperature. Now, here's something else. When you bake, the reason they tell you 350 or 425 is not just for how long it takes to bake, but some things like caramelization only happen at certain temperatures. And so here you wouldn't have caramelization at all because it's not high enough for that chemical reaction to occur. So of course, the lower the temperature, the less collisions, and the less they're going to bake. 2. Describe one way to increase the rate of the following reaction other than increasing temperature or adding a catalyst. So we have silver nitrate, aqueous, dissolved in water, plus sodium chloride or salt, also dissolved in water. That's that AQ, aqueous, yields sodium chloride and aqueous sodium nitrate. Okay, hit pause, and the answer is the reaction does not involve gaseous reactants. So increasing pressure will probably not affect the rate. Okay, so we just use pressure when it's a gas and we can squeeze it together. The reaction also does not involve solids. Remember, they are both aqueous, so increasing surface area doesn't apply because they're liquid. The reaction involves two solutions. Therefore, increasing the concentration of one or both of the solutions could increase the rate of reaction. Swirling the container in which the reaction occurred would also increase the reaction rate because you're adding more energy without increasing the temperature. You're adding the energy of mixing them around. Describe two ways to decrease the rate of the following reaction other than decreasing temperature. We have solid carbon plus oxygen gas yields CO2 gas. hit pause, and go ahead and hit pause and read the answer yourself because I'm running out of time.